the speaker is here, the slides are here. So we continue our...
except Sergey and the speaker should mute their sound.
Yeah, please mute your microphones.
Yeah, it would be great. Thank you. Thank you. Okay, so we continue our memorial conference for our great friend Alexey Zykin. And so the first speaker today is Sudhir Ghorpade from Bombay, who will speak about old and new conjectures on the numbers of points in algebraic sets over finite fields. So please, and the talk is about 1 hour.
Okay. Thank you. So shall I start? Very good. So, so I want to say first of all that this is for Alexey, and this is actually the second talk that I dedicate to Alexey. The first was in AGCT 2017, just a few months after he passed away. And I'm very glad and thankful to the organizers, Evgeny, Misha, and Sergey, for inviting me to speak in this memorial conference. I think Alexey would have liked this, so because Evgeny said that that was the criteria for speakers and topics, and I hope he's listening somewhere and maybe he appreciates. So I think my talk is going to be very, very concrete for most part, and I'm going to start. You know, as the title said, I am going to talk about number of points of algebraic sets over finite fields. And of course, most of you are familiar with what happens with varieties over finite fields. So, so let's maybe take a minute to just remind ourselves about the classical facts. I'm not going to use them directly, but just to have them in the background. So suppose I have a projective algebraic variety in projective M space defined over FQ, and the dimension is n. And I denote by P sub n the number of FQ rational points of the projective space, which is the well-known number q to the n plus q to the n minus 1 all the way down to 1. Then we have, so suppose we want to estimate the number of FQ rational points of X, or maybe vis-a-vis the number of FQ rational points of the projective space of the corresponding dimensions of P sub n. And one of the oldest estimate is the so-called Langevin inequality, which says that for my variety which is sitting inside Pm, I can talk about the degree. Suppose the degree is d, then the number of FQ rational points differs from the number of FQ rational points of Pn by d minus 1, d minus 2 into q to the power n minus half, plus constant times q to the n minus 1, where c is a constant which depends only on the m, which is the dimension of the ambient projective space, n, which is the dimension of the variety, and d, which is the degree. In other words, it's independent of q. Okay. Of course, if the variety is nicer, smooth, and so on, now we have well conjectures, and they give you somewhat better estimates. So probably one of the first corollaries in the famous paper of Dallin, where he proved the Riemann hypothesis, is this inequality for smooth complete intersections, which says that if I have a smooth complete intersection in Pm again of dimension n, then the number of FQ rational points differs from the number of points of the projective space of that dimension by a constant times q to the power n over 2. Of course, when you are looking at curves, it's a sort of an accident that n minus half is same as n over 2. But in general, this n over 2 is much, much sharper than n minus half, as you can well imagine, in higher dimensions. And where what is this b prime n? This is the almost like the Betti number. So in the case of curve, it will be twice the genus. Strictly speaking, it's the so-called nth primitive Betti number of x, which is the nth Betti number of this non-singular complete intersection. And you either subtract 1 or not, depending on whether n is even or odd. And just want to remark that this is something which is known explicitly. For example, one explicit formula, which probably goes back to Hirzebruch, is what I have in this slide here. I'm not going to try to read it, but just the point that if you know the dimension, you know so R would be the number of equations, which because it's a complete intersection, it will be like m minus n, and then you know this number explicitly. And
I'm sorry. So in the Linz result, is it necessary that the variety is a complete intersection, or it's just
bound? Yes, it is necessary.
It is
so
necessary.
This is I'm saying what he proved. Of course, the Riemann hypothesis, that is something for smooth projective varieties. I'm not talking about. This is a corollary of that, and that is for complete intersections. Yes, indeed.
Thank you.
So, of course, we know some, it's been a while, we know some extensions. So, for example, this is something I just mentioned, but I'm not going to talk about it. One has a, excuse me, get a message that, are you able to still see me and hear me? Okay.
Yes.
Okay, thank you. So yeah, for example, the constant C Langenwell do not tell us how big that can be and so on and so forth. So maybe one like to have an explicit bound so as to get an effective version of Langwell. Or what about this the Linz inequality for possibly singular complete intersections and so on. So we did that with Jill Leshow many years ago. But I just want to sort of emphasize that most of these results always assume that the variety is a variety, it's irreducible, okay? And I'm looking at the case when X is possibly reducible. In other words, X is a projective algebraic set. You could also look at affine algebraic set. And do we have good estimates for the number of FQ rational points of X? And that's the question that I want to address. And
sorry, but so by irreducibility, you mean reducibility over FQ or over FQ bar?
Well, over FQ doesn't quite make sense. Over FQ, it's a finite set. So I'm looking at over FQ bar, and as a variety over FQ bar, it is reducible. Yeah.
Thank you.
Yeah, sure. Okay. So now, typically, a reducible variety will have more points than irreducible variety of the same dimension. I mean, or it can have in any case. And so I want to start with probably the simplest case. So let's say, suppose
Let me ask a question, one more question.
Yes, please.
I understand that if it is irreducible over FQ, but reducible over FQ bar, then all FQ points are in the intersections of the components, right?
Mm-hmm.
And so you just have to count how many, so it's just simple Bezout theorem. So what is...
Not quite, not quite. Okay, so right. I will paraphrase this question. So let me put it this way. Suppose I give you a bunch of polynomials of given degrees with coefficients in FQ, and I ask you, say a bunch of homogeneous polynomials, and I ask you how many common zeros that they have, okay? So I can possibly, I mean, one way could be I can try to form the variety and try to estimate that. Another way could be that, I just sort of look at this combinatorial data and see if I can get good estimates on the maximum number of zeros that this can have. So this is let me illustrate this with a simple example. Maybe I'll come back to your question if you don't mind. Yeah. So let's say, suppose I have just one polynomial in m variables, coefficients in FQ, so little f of x1 to xm. And then how many zeros it can have? Well, of course, so for example, if it was just polynomial in one variable of degree d, it has at most d roots. We learned that in school. And when you're over the finite field, this will have d times q to the m minus 1 zeros, and that's a bound. Of course, it's a stupid bound if d were bigger than q or something, because then d times q to the m minus 1 is bigger than the number of FQ rational points in AM itself. But if
D is the degree, yes.
D is the degree. D is the degree. Yes. So yes, I should have said D is the degree. Thanks. But if D is less than Q, or especially substantially less than Q, this could be an interesting bound. And this is not only an upper bound, but it is attained because it's very easy to write down a polynomial in m variables of degree D, which has exactly these many roots. And you just think like a polynomial in one variable, take D distinct elements A1 to AD, and just form this product x1 minus A1 to x1 minus AD, and think of it as a polynomial in m variables. So of course, x1 can take D values, whereas the other variables are completely free. So and that probably goes back to Oystein-Ore in the 30s, this observation. And it's not difficult to show. You can sort of do a double induction on degree or and the number of variables and so on. Okay. And I want to now talk about the case of projective hypersurface. So let's say concretely, I have a homogeneous polynomial, non-zero homogeneous polynomial in m plus 1 variables of degree D. And I look at the corresponding hypersurface in Pm. So then I want to know what is the maximum number of projective zeros that this polynomial can have in PMFQ. And of course, a natural guess, if you were to sort of look at this array, is this would be D times the number of points of m minus 1 dimensional projective space. And a heuristic of that is you can just take your x and project it onto Pm minus 1 over, there are sort of P sub m minus 1 FQ rational points in the m minus 1 space below. This is a degree D variety. So over each point, there are at most D points. So you kind of guess that the maximum number of points on X, FQ rational points on X would be D times Pm minus 1. This is not completely rigorous, but you can make it into a rigorous proof. And then you wonder if this is a best bound. And again, this is a sort of silly bound if D were, say, Q plus 1 or more, strictly larger than Q, because this D times Pm minus 1 would be like Q times Pm minus 1 plus Pm minus 1. And you can see that that's bigger than or equal to P sub m. And so that bound is interesting if D is less than or equal to Q. And is it attained? Well, we can try the same example we did a moment ago. We had x1 minus a1, x1 minus ad. You homogenize that, and you would get something like this, a homogeneous polynomial of degree D. How many zeros does it have? Well, there are two possibilities. X0 can be non-zero, so I can take it to be 1. Then it's just like the affine situation. Then x1 can take D values, and x2 to xm can take arbitrary values. So that's D times Q to the m minus 1. Or x0 can be 0, and then this polynomial is x1 to the D. And so if this has to vanish, then x1 has to be 0. And then you have as many points as those free variables up to proportionality. So that's Pm minus 2. So the number of FQ rational points here is dq to the Pm m minus 1 plus Pm minus 2. And that, of course, is same as Pm minus 1 if D is equal to 1, but if D is larger than 1, then
sorry, question. Can you recall what is P minus 1?
Yeah.
Maybe it's on the previous slide, or P minus 1.
Sure.
Pm minus 1, yeah.
So I kind of defined Pn right at the beginning here. Q to the n
thank you.
plus all the way up.
It's okay.
Now that you asked me, let me also mention as a convention, this P sub n, if n happens to be negative, I set it to be equal to 0 by convention, which is of course natural. But if n is non-negative, it will be a positive integer, and it is or you can write it as Q to the n plus 1 minus 1 whole thing divided by Q minus 1, right? Yeah, thanks.
So I didn't understand. Do you claim that the natural guess is correct or not? Maybe not optimal.
No, so I'm saying that the natural guess is correct, okay, but it's not a good guess.
Not optimal.
In the sense that it is not. It is certainly it is not attained. I mean, I've not proved that. I've just said that it is not attained for this particular polynomial, which would look like a natural optimal animal. But in fact, it was, I guess, Misha Fassmann who conjectured that that's in fact the best upper bound for the number of FQ rational points of a projective hypersurface, namely dq to the m minus 1 plus Pm minus 2. So every, so I said it in the language of polynomials. If I have a non-zero homogeneous polynomial of degree D, let's say D is equal to Q, then the number of FQ rational points, I may not write parenthesis FQ every time, number of zeros in PMFQ of this is bounded above by dq to the m-1 plus pm-2. And since I already gave you an example of a polynomial which has these many zeros, that shows in fact that this is a upper bound is in fact the maximum value. So it's a maximum cardinality of this where f is varies over all homogeneous polynomial of degree d in m+1 variables. Okay. And this somehow caught the attention of Serre, and he quickly gave a proof to confirm Misha's guess. So this is, and I was going to sort of go over this proof, which is not very long and it's quite beautiful, except I fear I may run out of time. So I think I will skip it for the time being, but come back to it if there is time and interest. So I mean, he sort of, okay, so this is just, so allow me to, so that's the, okay. So the proof actually shows when the bound is attained, when you have lots of zeros, where you have your hypersurface is a union of d hyperplanes with lots of things in common, with the m-2 dimensional projective space in common. So, all right. So now, so after this, people were interested in sort of extending this in many ways. And there are two important conjectures that came about. So one way is, see, I mean, there are, you can think of a hypersurface in two ways. One is that it's something defined by a single equation. Another is that it's a codimension one subvariety of the, so of the projective space, let's say. So in some sense, thinking in these two different ways suggest two generalizations. So the first one was the generalization where instead of one polynomial homogeneous of degree d in m+1 variables, suppose I take several polynomials which are homogeneous, and let us assume that they are all of degree d, and I'm interested in the maximum number of common zeros. So, and I will assume that these polynomials, let's say f1, f2, fr are linearly independent. So then of course that puts a limit on how many polynomials I can take. The maximum number of polynomials I can take would obviously be bounded above by the vector space dimension of the space of homogeneous polynomials of degree d in m+1 variables, which is the well-known binomial m plus d choose d. So in this setting, what I like to call Fassmann-Boguslawski bound or conjecture, they made the following curious conjecture. And let us try to understand this. So what they say is that suppose I have R linearly independent polynomials, homogeneous of degree d in m+1 variables. I'm assuming d is sort of less than q minus 1. And suppose I look at their common zeros in PM. So I look at the corresponding algebraic set, if you like. Then, so just let's jump to the last line. Then this number of FQ rational points of that set is bounded above by this explicit combinatorial quantity, which involves the number of points of projective spaces and some coefficients here, nu sub I. So what are these coefficients? I'll explain this. So what you do is you look at exponent vectors of monomials of degree d in m+1 variables. So if you like tuples I1, I2, im+1, which add up to d and consist of non-negative integers. And let us suppose so that's a collection of m plus d choose d tuples. I ordered it lexicographically, and I look at the biggest one first and the next biggest and so on. And when I have R polynomials, I look at the tuple which is rth in this ordering. And that's what I have called nu1 to nu m+1. Okay. And let us suppose J is the first I for which nu sub I is not 0. Then the conjecture was that this is bounded above by this PM minus 2J, so J coming from this minimum, plus summation nu I PM minus I minus PM minus I minus J. A remarkable guess, I would say. In some sense, the right-hand side is something which is purely combinatorial, but it serves as as a bound. In fact, the more precisely, I think they expected that this to be a exact bound. That means it is met. So so in fact, what they conjectured was the maximum value of the number of FQ rational points of common zeros of R linearly independent homogeneous polynomial in m+1 variables is given by this quantity. So we will see in a minute whether that's true or not. But since I'm going to use this quantity on many occasions, let me use this notation E sub R dm. Now it will denote for me the maximum number of zeros in PMFQ that are linearly independent polynomials homogeneous of degree D can possibly have. Okay.
So, sorry, could I ask you, so could you clarify please a bit? So in this conjecture, does one assume that the intersection is a complete intersection such that the dimension drops each time by one? No.
No geometric hypothesis. Only thing is which is being assumed is that the polynomials are linearly independent. If they were not, you throw away the dependent. So that's yeah. So this is like, I mean, this is a generalization when you think of a hypersurface as something given by a single homogeneous polynomial of degree D. Okay, so I'll illustrate this. So let us look at the case of one polynomial. So R is equal to 1. So what am I doing? In that recipe, I'm looking at the first tuple in the list of exponent vectors of monomials of degree D. I'm ordering lexicographically, so I'm looking at the biggest guy. And you know the lexicographic order gives greater preference to the earlier coordinates. So the biggest one lexicographically would obviously be the tuple which has D in the first coordinate and 0 elsewhere, because things have to add up to D. And so this D, comma 0, 0 would be the largest tuple. So if you sort of translate that, so my J is going to be 1. So this is going to be PM minus 2 here. And there is only one non-zero term, which is corresponding to I equal to J equal to 1. And that new one is D. And I will have D PM minus 1 minus PM minus 1 minus 1. So that's PM minus 2. So that, of course, is Q to the M minus 1. So you see that here you would get exactly D Q to the M minus 1 plus PM minus 2, which was the Sayre's inequality. What happens if R is equal to 2? You look at the second tuple. So let us, to avoid trivialities, let's assume that D is bigger than 1. Then if you can't put D, the next best you can do is you put D minus 1. And then you need to put a 1 somewhere. You put it as early as possible, put it in the second coordinate. So that's the second tuple lexicographically. And so that's your new one. And if you just work out that bound, you will see that you would get D minus 1 Q to the M minus 1 and plus Q to the M minus 2 plus P sub M minus 2 and so on. So that's the sort of unpeeling of that formula. Very good. So what happens after this? Oh, okay. So now since you asked me about complete intersection, I would like to say that around the same time, there was another conjecture. And this conjecture actually has a happy ending in the sense that it was turned out to be true. And that's sort of thinking of a hypersurface as a complete intersection, if you like. And this is what Alan Cowrer proved. And you can think of it as some kind of a counterpart of the Fassmann-Boguslawski conjecture. So I have stated the theorem of Cowrer, which is the following. So suppose I have a, so in fact, okay, so just look at the last part of this, which was the original conjecture. That suppose I have a equidimensional projective algebraic set in PM defined over FQ, and I'm given the dimension, the geometric dimension n, and I'm given the degree, say delta. Okay. For example, this could be a complete intersection, and then this degree would be the of the variety would be the product of the degrees of equations if you took the right number of equations. So then the conjecture said that this number of
sorry. What is non-degenerate algebraic set?
Non-degenerate means it is not contained in a hyperplane.
Thank you.
Okay. Thank you. So so if it is a equidimensional non-degenerate algebraic set of dimension n and degree delta, then what was conjecture was that this number of FQ rational points is bounded on the right by delta times p sub n minus delta minus 1 times p sub 2n minus m. And so you will see that this is really interesting bound when the dimension is large, which is really the case when you have a hypersurface. The dimension is pretty large vis-a-vis the dimension of the ambient space. It's just m minus 1. And so this is kind of interesting when little n is sort of bigger than m by 2, for example. So I just want you to look at a very special case. Suppose codimension is 1. Oh, why did I write codimension? Okay, so suppose suppose codimension is 1. So it's like a hypersurface. So which means n is m minus 1. Then if you substitute that here, you would see that you would get Pn minus, what would you get? So 2m minus 2 minus m. So m minus 2. So Pm minus 1 minus Pm minus 2, that's q to the m minus 1. And here you will have Pm minus 2. So you just get the Sayre bound when it is hypersurface. What Alan proved is a more general version where instead of assuming equidimensional, he says that, well, suppose I'm given irreducible components and I know their dimensions and I know their degrees, then it is bounded on the right by this quantity. Okay. He calls it the conjecture of Ghorpade and Lashu, but really speaking, it should be attributed to Lashu, who had it much earlier, although it was published in our joint paper that I mentioned a while ago. Okay, so that's one kind of generalization, and since this sort of settles, I'm going to mainly talk about the Fasman-Boguslawski. Okay. So, but perhaps we can compare the two. So, roughly speaking, the hypothesis of the Fasman-Boguslawski conjecture is something that you can sort of easily verify. I mean, you in practice, you're often given polynomials, you know what their degrees are and the number of variables. And so say you have just R linearly independent polynomials in m plus 1 variables of a given degree D. And so in the cases where the two things coincide, for example, so I have something given by R linearly independent polynomials, homogeneous of degree D, and suppose it happens to be equidimensional, then this bound will be typically better than the Fasman-Boguslawski bound. So so I'm just so for example, so I have a complete intersection. If that common zeros form a complete intersection, the degree will be then the product of the degrees of the equation. So that's d to the power r. And if you substitute delta equal to d to the power r in that, then you can actually show that, this quantity here fares a little better than the corresponding Fasman-Boguslawski bound. On the other hand, if your variety is not equidimensional, you have then the Fasman-Boguslawski bound can be better than the Kovrov bound. I'm just taking the example of, say, R quadrics, all of degree 2, just x0, x1, x0, x2, x0, xr. And if you look at their common zeros, so that has a big projective linear space in common. And you can see that the number of common zeros is actually given exactly by the Fasman-Boguslawski bound, which works out to be Pm minus 1 plus q to the m minus r. On the other hand, if you kind of follow the Kovrov bound, then it will be sort of much bigger than this, because you will have a bunch of other terms. So in general, the two bounds sort of complement each other, and neither implies the other, so to speak. Okay. So with that, I want to go ahead and discuss further results on this Fasman-Boguslawski. So the first case, of course, was basically says inequality r equal to 1, and the next progress came about with Boguslawski in a paper in 1997, where he proved that the conjecture is true if r is equal to 2. So in other words, this E2dm, the maximum number of zeros of two homogeneous polynomials linearly independent of degree D in m plus 1 variables, is given precisely by this quantity, which was conjectured by Passman law. And the proof is much more intricate than that of Serre-Bound, and it sort of uses Serre-Bound uses reduction to certain complete intersection and this what I call a basic inequality, some kind of a affine Bezout type of result. Also not affine Bezout, so you can a basic bound, let me put it that way, which again is due to Lachaud. Okay, and then so the conjecture.
I'm sorry, and so the heuristic proof of Lachaud's inequality is just projection from a point again. Yeah.
The heuristic proof is exactly that.
And the hard part is probably when there is no a point outside variety.
That's right. But you can find a rigorous proof in our old paper. There are many other proofs also. Okay. So then it kind of remained open for a while, and but before I come to further progress, I want to point out the affine analog. Remember, when I mentioned the case of affine hypersurface, that was somehow easier than projective hypersurface. So you can ask a similar question for affine algebraic sets. What does that mean? That means suppose I have R linearly independent polynomials, each of degree D, in M variables, coefficients in FQ, and I ask what is the maximum number of common zeros they can have in the affine M space over FQ. Okay, and Heinen and Pelikan in roughly around the same time as Boguslawski proved that this number is given by this kind quantity, which I have called HRDM. So what is that? That is Q to the M minus summation of 1 plus summation of alpha M minus I plus 1, Q to the I minus 1. I'll have a different expression for this in just a minute. This was the original formulation of Heinen-Pelikan, where this alpha 1 to alpha M is somewhat similar to that nu 1 to nu M plus 1. It's the rth tuple among M tuples with coordinates not exceeding Q of non-negative integers, which satisfy this kind of inequalities, that their sum is bigger than or equal to M into Q minus 1 minus D. And you arrange them in ascending order now, the smallest first and then bigger and so on and so forth. So you take the rth guy there, and that determines this quantity inside the parenthesis, and you subtract that from Q to the power M, and that in fact they proved is the correct maximum. Okay, so just want to illustrate this. So for example, again, if I take R is equal to 1, then what was that condition here? I want the sum to be bigger than or equal to M into Q minus 1 minus D. And so I want the first tuple. So I want, so you see, and this beta i's are at most Q minus 1. So if I want the smallest one, so I should take, so I will need, I will need the sum to be bigger than or equal to this. Let me say D is less than Q minus 1. Then I would have to sort of take Q minus 1 copies of, M minus 1 copies of Q minus 1 and put Q minus 1 minus D in the first coordinate. So if you think about it for just a minute, you will see that that's the first M tuple which satisfies the condition. So if you plug in that, you would have, so let's see, so I is equal to 1, you have alpha M, that's Q minus 1. So all the way up to 1 to M minus 1, you will have Q minus 1 times Q to the I minus 1. And I is equal to M, which is alpha 1, that will give you Q minus 1 minus D. You multiply that by Q to the M minus 1. And when you add it up, this is a telescopic sum here. You will see that you actually get D times Q to the M minus 1, which is Ore's inequality. And the proof of this is somewhat involved. It uses things like Kruskal-Katona theorem and so on. So just want to make a remark that probably a nicer way of writing Heinen-Pelikan formula is by realizing that you can also write it as summation, let me say beta I Q to the M minus I, where beta 1 to beta M is the rth element, again now in descending lexicographic order, biggest first, among M tuples of non-negative integers satisfying the sum is less than or equal to D. Now it looks more like the Fassmann-Boguslawski description, but I have less equal here. And So, and then sort of, I look at the not necessarily homogeneous polynomial in m variables of degree less equal to d, linearly independent. This is also a vector space of dimension m plus d choose d. And if I look at the maximum possible number of zeros of common zeros of R such polynomials, then that number is given by this HRDM. So it's a very concrete quantity. And so this, there is a nice proof of this, which is probably easier to follow, more recent by Peter Billen and Mrunmayee Datta in not too long ago. But the theorem is actually due to Heinen-Pelikan. Okay. So where are we? So the case of R is equal to 1, R equal to 2 are known. The affine case is known in full generality. What about the projective one? And there, okay, so maybe before I do that, let me just sort of say there is another way of looking at the same thing. So when you're trying to find the maximum number of common zeros of R linearly independent polynomials, that same thing as looking at maximum number of FQ rational points in sections of the Veronese variety. So you just take the dipole embedding of PM in this big projective space and look at the image and you cut it by linear sections, say of codimension R, and you ask what is the maximum number of FQ rational points. This is exactly same as that. And if you like this sort of an approach, you can also play similar games with other classical varieties other than Veronese, like the Grassmannian, Schubert, and so on. So I have looked at that, but I'm not going to talk about it here. So I want to report something which I actually mentioned in the conference for 60th birthday of Misha and Serge Vladut in Moscow, which was progress on this Fassmann-Boguslawski conjecture. So with my former student, Mrunmayee Datta, we proved that so we sort of looked at the first non-trivial case, D equal to 2, the quadrics, and we showed that the conjecture is true, provided the number of equation is at most the number of variables. On the other hand, already for the quadrics, it can be false if the number of equations is more than the number of variables. So if R is strictly greater than m plus 1. In this case of quadrics, of course, R is bounded above by m plus d choose d, which is m plus 2 choose 2. So it is actually false for at least these many values. And really speaking, this was realizing that this is something which was done by Zanella, an Italian mathematician. But we persisted with the general case, and eventually we proved that the conjecture is true, not only for the quadrics, but for any degree d, and assuming again that d is less than q minus 1, as long as the number of equations is at most the number of variables. If R is less than or equal to m plus 1, the conjecture is good. Otherwise, it is false. And this last theorem would use Serre's inequality, but doesn't use Boguslawski. So if you like, Boguslawski's theorem is a corollary of this because it's for R equal to 2. Okay. So,
Excuse me. So
yeah.
This is the sharp estimate for R, right?
Yes. So when I say the conjecture is true, I mean that the maximum value, this ERDM, is exactly given by TRDM, the conjectured Fassmann-Boguslawski bound. That's what I mean. And when I say conjecture is false, I mean the maximum value is not given by the conjectured value. So I don't necessarily mean that the conjectured value may not be an upper bound. It might still be an upper bound, but it won't be the best upper bound. Is that clear? Okay. So let me just sort of elaborate on what I was saying about the proof for just a moment. So really the idea was to use a work of Zanella, which he had done in a different context, in fact, motivated by cryptography and so on. So he was interested in linear section of quadratic Veronese varieties, where he analyzed linear sections of quadratic Veronese variety. So he looked at quadratic tuple embeddings, if you like, of PM in PM plus 2 choose 2 minus 1, And he said that if I intersect that with the linear subspace of codimension R, then this is bounded above by this, what I like to call Zanella bound, which is given, okay, it is slightly technical, some kind of number of points of a projective space, plus an, so to speak, an error term, which is the floor of some power of Q, where this epsilon is, okay, so I have defined quantities delta sub t, t plus 2 choose 2. So delta sub m will be the m plus 2 choose 2. So R will be less than or equal to delta m. So if I have anything R which is less equal to delta m, there'll be a unique case so that it is sandwiched between delta m minus delta k and delta m minus delta k plus 1. Okay. And so you take that k and you look at p sub k plus the floor of this q to the epsilon minus 1, and he showed that this section is bounded above by that. And essentially the way we showed that the conjecture is false was to show that this Zanella bound beats the Fastman-Boguslawski bound in the case of quadrics when the number of equations is larger than m plus 1.
So sorry, I'm lost. So the Fastman-Boguslawski bound was the bound for the left-hand side by the number t, but then if
TR2m is the Fastman-Boguslawski.
Yeah, but then if ZR is less than TR, then the number of points is less than TR, and this.
Yeah. So when I say it's false, when I say that, what I mean is this is not the maximum value. It may be an upper bound.
To show it's not optimal. I see.
Yeah, it's not optimal. Exactly.
So that was what you was claiming, that the conjecture is false, that it was not optimal. Yeah.
That's right. That's right. So when I say conjecture is false, what I mean is that it is the exact maximum is not given by the conjecture.
And later you will comment whether it is true that the equality holds.
Sorry?
Probably later you could comment whether it is true that the equality holds. So is it true that the equality holds in Boguslawski's Fastman conjecture for all R?
No, it doesn't. In fact, that's what this theorem 1 says, that the equality does not hold. Already in the case of quadrics, when the number of equation is more than the number of variables, R is strictly larger than m plus 1.
No, Sudhir, the question was different. The question is, in that conjecture of ours, is it true that the inequality is correct?
Okay.
Yes, thank you very much, Michael.
Yeah. Okay. So that is probably true, at least in this case of quadrics. I'm not sure if it is true in general.
Thank you.
But I was I've been more interested in knowing the exact value of that number. So in that sense, it is false. Yeah. Okay. On the other hand, not only the inequality, but the equality is also true, not just for quadrics, but for any degree d less than q minus 1, as long as the number of equation is at most the number of variables. That's what we proved sometime later with which is in the proceedings of AMS. So the first one is, by the way, in the whatever for the Misha birthday conference paper. Okay. So yeah. So I guess I remarked about this proof of theorem 1, and I want to say something about theorem 2, which is a positive theorem. And so first of all, you can actually translate that nu1 to nu r when R is less than or equal to m plus 1. The Fastman-Boguslawski bound can be explicitly worked out as d minus 1 q to the m minus 1 plus pm minus 2 plus the floor of q to the m minus r, which almost all cases, if R is less than or equal to m, you can just throw out this floor. But if R is equal to m plus 1, then this quantity will be 0. You remember in the Boguslawski's theorem, it was q to the m minus 2. So you just replace that by q to the m minus r and floor it down in case R is m plus 1. So what does the proof use? It does use the inequality of Sayre. So for hypersurfaces, it uses the theorem of Heinen-Pelikan, the basic bound that I mentioned, and some combinatorial version, what I like to call a co-prime closed family of polynomials and their characterization, and some case-by-case analysis. And of course, when you want to show that the equality holds, you need explicit construction of maximal families. So you put all that together and you get that. But that's already a little bit of an old story, because this is almost 5 years ago, although this paper was published 3 years ago. And so what is next? So what is next is that, well, I was interested in the finding E sub r dm. And what have I done? I have told you what it is when r is less than or equal to m plus 1. And you can do some tricks, and you can also, so you kind of, you can also figure out what is it when r is very large. So for example, if it is m plus d choose d, or m plus d choose d minus some small numbers. So what you don't know is these values when r is bigger than m plus 1 and is somewhat smaller than m plus d choose d, or less equal m plus d choose d minus d minus 1. And if d is equal to 2, we know it completely thanks to Zanella. And of course, we have always looked at the case of d less than q minus 1, but you could also ask about the case of d bigger than or equal to q minus 1. And partly to sort of to make, we sort of made a educated guess in this case. So there is a conjecture that Mrunmay Datta and I made in our paper, which I like to call incomplete conjecture. And that is the following. So let me explain what is that. So first of all, I'll say, so remember this R, which is the number of equation, typically goes from 1 to m plus d choose d. And in this conjecture, I'm assuming that R is less than or equal to m plus d minus 1 choose d minus 1. So this is a quantity which is less than m plus d choose d typically. So that's why it's not giving you a conjectured values for all values of R, but several values of R. And there we conjectured that this ERDM is simply given by the corresponding affine quantity for affine M space, but degree 1 less, and add to that the number of points of a projective hyperplane in PM. So P sub M minus 1. So it looks very tempting that somehow you can take the projective thing, reduce it to affine, and deduce it, but it's not so straightforward. At least we don't see how it can be done very quickly, even when you know the general result in the affine case, because the degree is also going down and so on. So that's what it is. So notice that this HR d minus 1m would be well defined as long as R is less than or equal to d minus 1 plus m choose d minus 1, and that's consistent with the hypothesis that I put on R. Okay, so that was the conjecture we made, and if R is less than or equal to m plus 1, it just reduces to this theorem 2 here, yeah, this one. But if R is bigger than m plus 1, it's something other than what Passmann and Boguslavsky conjectured. And so since we had done earlier for R is less equal to m plus 1, we pushed that more with Peter Bielen also. And then we proved that this new conjecture is true if R is less than or equal to m plus 2 choose 2. So that's significantly better than m plus 1. And we also covered the case when d is equal to q minus 1. Earlier, we had d less than q minus 1, but we have this now for d less than q. And well, d equal to 1 is kind of trivial. So I have avoided that because I want to get a positive integer here. So that's what Peter and I proved. And it was somewhat, I mean, it was, okay, so what did it involve? So incidentally, when R is less equal m plus 2 choose 2, you can work that quantity out explicitly, the one here, HRD minus 1 m plus PM minus 1. You can spell it out. It comes out to be d minus 2 into q to the m minus 1 plus PM minus 2 plus the floor of q to the m minus I and floor of q to the m minus j. But what are these I and j? Well, these I and j's are unique positive integers, I less equal j less equal m plus 1, such that your R is of the form I minus 1 m minus this. I mean, it looks a little strange, but I will sort of hopefully explain to you why this kind of a thing is natural. So if, you know, so that's what is proved for R less equal m plus 2 choose 2. And we had to use, of course, again, Serre inequality, Heinen-Pelikan, a full strength of Zanella's theorem, and very conveniently some kind of a version of Bézout, which Gilles Lechoux and Robert Roland proved in 2015, and a very nice, tight inequality of the Japanese mathematicians, Uma and Kim, about number of points on hypersurfaces which don't have a FQ linear component. So using that, we could push it this far. And then somehow we couldn't do more than that. And so we were interested, and then we decided to follow a completely different approach. So how much time do I have? About 5 minutes, maybe?
Yes, you do have 5 minutes, definitely.
So I would like to explain what I like to say, this completing the incomplete. So we had this incomplete conjecture here, and which is only up to R less equal m plus d minus 1 choose d minus 1. It does cover a lot of values of R, but not all. So how do I do that? And so a starting point is this simple binomial identity. You notice that you can write m plus d choose d as m plus d minus 1 choose d minus 1. And so your denominators are, numerators are going down by 1, and you go up to, so this could be an exercise for undergraduate students at independent university, maybe who should be able to do it in 5 minutes. But this is kind of a motivation. So the first term here was the bound up to which we had the older conjecture, m plus d minus 1 choose d minus 1. But then there are the other terms and so on. Okay. And now if I have some number R, which is between 1 and m plus d choose d, for a moment I'll assume R is strictly less than this, then it's easy to see that you can sort of, what you can do is you can take this sum, and you look at the sum, you go as far as you can. So you can write it as sum of the first, let's say, I terms in this sum formula here, plus some remainder, which should be smaller than the next term in that big sum above. So I can find a unique I and unique j, so that j is less than the next guy in this sequence, and I is like that. So for example, if R happens to be less than this quantity, less than or equal to this quantity, then this I will be 0 and j will be just that. J will be R. Okay. So, and what happens if R is m plus d choose d? Well, in that case, you take I is equal to m, and j is equal to 1, which is somehow natural to do. But very good. So okay. So what have I done? For any number R, I have associated unique numbers I and j with this sort of property. Very good. Now, the complete conjecture is simply the following, that if I have any R between 1 and m plus d choose d, and if I and j are as above, then E sub R dm is given precisely by not HR, but H sub j. So this j coming from here, the remainder of d minus 1 and m minus I plus pm minus I minus 1. So you notice that if R is less equal m plus d minus 1 choose d minus 1, j is R and I is 0. So it is exactly the incomplete conjecture. So this is the complete conjecture that the three of us made. And as I just said, it reduces to the incomplete conjecture when this. And so that we believe is the correct exact maximum of this D linearly independent, R linearly independent homogeneous polynomial of degree D in m plus 1 variables. And what do we know? Oh, by the way, we can also write an explicit version of that. So if you are familiar with this Macaulay's theorem in commutative algebra and so on, related to Hilbert function, there is something called D binomial expansion. So I take the number m plus d, choose d minus r. Then there is a unique way to write it as sd choose d plus sd something choose d minus 1 all the way something choose 1, where these numerators are strictly decreasing non-negative integers, and they're uniquely determined by the left-hand side. And if you know these coefficients in the D binomial expansions, then you can write down this P sub R dm in this fashion, the P sub SD, which is here, minus D, and then this floor sub bunch of power sub Q. It's slightly complicated to get a grip, but it's completely elementary and completely explicit. Anyway, so that's just another version of this conjecture. And what do we have? What we proved is that what we conjectured to be an exact value is always a lower bound. So ERDM is always greater than or equal to this. And we proved an upper bound, which is something like Heinen-Pelikan or projective version of Heinen-Pelikan. So we proved that it is less than or equal to what I call KRDM, which is AI PM minus I minus 1. If you remember, the Heinen-Pelikan was some kind of beta I q to the m minus I. So here I have AI PM minus I minus 1, where A0, A1, AM is the rth element in descending lexicographic order of all m plus 1 tuples of non-negative integers that add up to D. So we have a lower bound as well as upper bound in general, and lower bound in fact is the conjectured exact value. And there are some happy cases when the lower bound and upper bound coincide. And then of course you get the conjecture to be true. Using that or otherwise, we have sort of showed that earlier we had shown the conjecture to be true for R less equal m plus 2 choose 2, but we can also show this thing is true for m plus 1 times D additional values of R, namely these ones, where ER is a particularly simple quantity. So anyway, so that's the status, but I'm afraid the thing is open in general. I just want to say a word about what we use. So we use a more refined version of Kruskal-Katona, what is called Clements-Lindstrom theorem, and sort of its variants and extensions. And there's a systematic notion of what I like to call projective reduction of polynomials and a so-called projective footprint bound, and some Hilbert functions and vanishing ideals of projective spaces, and these Macaulay expansions or D binomial expansions. So we, if somebody is interested, there is a preprint on the archive, already 2 years old, should get published sometime, I don't know when. But there is another paper we wrote, which was sort of preparatory work for this, that's already published last year. And that's where you can find the details. So just want to end with the remark that the general problem is of course open, and if there are young people, that could be something interesting for them. So that's it. Thank you. These are my collaborators, Peter Bielan to my left and Mrunmay Datta. And you know, this was back in the days when people can meet in person and work on a blackboard and so on, and not have to do this webinar, etc. But that's just about it. I think I should stop here. I had one more slide, which was last email I got from Alexey. If people are interested, I can show them that.
Yes, please go.
Okay.
So anyway, so you know, Alexey, of course, it's somebody. Probably I should say this in the later part of this thing. Is someone I knew since his undergraduate days and was very fond of him. So in September of 2016, he wrote to me wanting to visit me in India, and of course I welcomed that. And then he writes, so we and then I suggested that maybe he can visit us from July or August 2017. And then he said, yeah, August would be perfect because I do something before that, etc., etc. And I'm working with so many different people. And he said, well, he's looking forward to coming to India and discussing mathematics with me. And well, as we all know, unfortunately, in the April of that year, when he was to visit, he died in that tragic accident. And so we could never really host him. But so anyway, thank you. Thank you.
Thank you very much. Let's thank the speaker. Thank you very much for this very interesting, very explicit and quite combinatorial talk. And I'm sure that Alexey would appreciate very much the content. So please, some questions.
Yeah.
Yes.
So, and how large is the difference between the upper bound and the lower bound?
Okay. So, okay, I guess the correct answer is I don't have a good estimate, but there are cases when they coincide, in fact. So maybe it's a good question to kind of estimate the difference, but it's not something which is always positive.
I see. And the second question was, how large is the difference between your bounds and the original conjecture?
Okay, so my guess is that our bound is a tighter bound. My guess is that your bound is probably still an upper bound in general, but the one that we have conjectured is a sort of an exact fit.
I'm asking because in your first counter examples, the difference was usually 1. Is it small or is it large? So that's the question.
It can be large, actually. It can be large. I mean, yeah, I mean, I guess the first counter example is 5 quadrics in P3 or something like that, I think.
Yeah.
And so I don't remember, maybe one of them was 1 plus 2q and another is 1 plus q square or something like that. But I can check this.